There's a 13-minute sequence at the start of Gravity that actually had astronauts writing op-eds. It wasn't because it was too scary, it was because somewhere in that 90 minutes of movie time, the film broke an orbital mechanics rule most viewers never noticed. That's the beauty and the danger of Hollywood physics. Welcome to Science versus Cinema. Today, we're taking that opening apart, piece by piece. We'll look at what NASA actually warned about back in 1978, and where Hollywood decided the truth just wasn't dramatic enough. Here is what happens on screen. Russia destroys one of its own dead satellites in a missile test. Nobody accounts for the debris. It hits a second satellite, then a third, and 11 minutes later, a wall of shrapnel moving faster than a rifle bullet rips through the Space Shuttle Explorer mid-spacewalk. Stone and Kowalski survive, but almost no one else does. Then, and this is the part that sticks with you, that same cloud comes back. 90 minutes later, one full orbit, and it takes out the ISS. 90 minutes after that, it hits the Chinese station, Tiangong. The core premise here is grounded in real science. It's called Kessler Syndrome, named for NASA scientist Donald Kessler, who published the theory in 1978. His point was simple. Low Earth orbit is a finite space. Pack enough satellites and debris into it, and eventually, two objects collide. That collision creates hundreds of new fragments. Those fragments hit other things. Each collision multiplies the debris count instead of just adding to it. A chain reaction, not a pileup. Credit where it's due, the film gets the basics right. Debris in low Earth orbit travels at 28,000 kilometers an hour. At that speed, a fleck of paint can crack a windshield, and a bolt can go through a hull like it's not even there. The zero-gravity movement, stone tumbling, losing orientation, the eerie silence of a hull breach, that was built with wire rigs and robotic arms to be physically accurate. That part isn't Hollywood exaggeration. That's just what it looks like. Here is where the science diverges. First, a real Kessler cascade doesn't happen in an afternoon. It plays out over decades, even centuries, as debris density slowly climbs. Compressing it into a 90-minute loop is a script decision, not a forecast. Second, and this is what astronomers actually flagged, that same cloud doesn't politely return every 90 minutes to hit the next target on the list. A single breakup scatters fragments across a spread of altitudes and orbital planes almost immediately. And third, the big one. Hubble orbits at about 559 kilometers, tilted 28 degrees. The ISS is nearer 400 kilometers, tilted 52 degrees. They aren't neighbors. A jetpack flight between them, the way the film stages it, isn't a stretch. It's a different neighborhood entirely. So the film compresses a slow-motion risk into a 90-minute thriller. Fair enough, that's what movies do. But don't let the compressed timeline make you dismiss the underlying risk, because that part isn't fiction. In 2007, China destroyed a weather satellite in an anti-satellite test and added over 3,000 trackable fragments to orbit overnight. In 2009, an active Iridium satellite and a dead Russian one collided by accident and added 2,000 more. Every one of those fragments is still up there right now, and every one raises the odds of the next collision. We're not watching a movie's timeline. We're watching the real one, just running quieter and a lot slower. And with thousands of new satellites launching every year, while low-flying constellations like Starlink have a fast death rate due to atmospheric drag, the real orbital junkyards are parked much higher, at 800 to 1,000 kilometers, where debris stays locked in place for decades. That's the layer where some researchers say the math has already crossed the point of no return, where collisions start triggering collisions on their own. The question NASA's debris office is actually asking isn't, could this happen? It's whether we're already standing inside the early stage of it.